Common optimization problems in economics. Most nonlinear functions that we'll work with have a maximum or a minimum point, and we can use first order and second order derivatives to find the value of x that either minimizes or maximizes a function. That's that second derivatives test. For example, find the level of output that maximizes profit, find the level of output that minimizes cost, find the combination of goods that maximizes utility. Optimization problems are inherent to economics, and actually you've been doing optimization problems all along in your 105 and in your 106 courses. Consumers maximize utility or satisfaction. Most common you see in 106 is producers or firms maximizing profits or minimizing costs. And in some instances, we look at problems involving governments trying to maximize tax revenue. And to an economist, optimization is all about finding the best value of something. So we'll work through the two most common single variable optimization problems, profit maximization and cost minimization. When you see an optimization problem in your economics courses, they typically involve three elements. In words, the objective function f of x is the function that's to be maximized or minimized. For example, the firm's objective is to maximize profit. Choice variable or variables, x, we're working with single variable functions, so we only have one choice variable. And the choice variable determines the value of the objective function. Example, the firm's objective is to maximize profit by choosing output. Output is a choice variable. And finally, any constraints that may restrict the values of the choice variables. For example, the firm's objective is to maximize profit by choosing output subject to output being non-negative. Let's take a look at how economists put this in mathematical notation. So in math notation, you'll see this. Max x, y equals fx, st, some constraints. So what does all of this mean? You need to be able to look at something like this and interpret it. Y equals f of x is a subjective function. It's a thing that we're optimizing. We're either maximizing it or minimizing it. In this case, we're maximizing it. This term here, the x, is the choice variable. So we're maximizing the objective function by choosing some x, and they're going to have some constraint. For example, maybe the value of x has to be greater than 0. So again, this setup is interpreted as the objective is to maximize f of x with respect to x, subject to some constraint. So let's take a look at a specific problem, max q pi q, such that q is greater than or equal to 0. So we interpret this as the objective is to maximize profit with respect to quantity, subject to quantity being non-negative. Quiz yourself. Write the following minimization problem out in math notation. A firm's objective is to minimize, min, total costs by choosing output subject to output being non-negative. Pause the video and try this on your own. So one way to write it is the following. We want to minimize TC of Q, where TC of Q is going to be that total cost as a function of quantity, by choosing some quantity such that quantity is greater than or equal to 0. Here's the objective function. The choice variable is Q, and the constraint is that Q must be greater than or equal to 0. Let's do another quiz yourself. Write the following maximization problem out in math notation. A firm's objective is to maximize average production of labor, APL, by choosing labor subject to labor being no greater than 100. Pause the video and try this on your own. So here we have our problem. We're going to maximize our objective function, which I've defined as APL of L, by choosing some level of labor, L, such that labor is less than or equal to 100, which is the constraint. So this is just a recap of the second derivatives test, which, if you recall, is just a way to find and classify stationary points of a function. So these are the steps you use. You first specify the first derivative of the function, set that equal to 0, and then solve for x. call the outcome x star. Then you evaluate f of x at x star, which yields y star. Then you specify the second derivative of the function. The second derivative is just the derivative of the first derivative. And then use the table below to classify whether the stationary point is a maximum, a minimum, or unknown. When it comes to profit maximization and cost minimization and other types of problems we'll be doing in this course, you're going to find a maximum or a minimum. So let's jump right into a firm's production decision using optimization techniques. So suppose we're given the following information. P is price, Q is quantity. The inverse demand curve is 126 minus 3Q. Total revenue, as always, is defined as price times quantity. Total cost is given to us as 5 plus 5Q squared minus 2Q. And profit is defined, as always, as total revenue minus total cost. Using optimization techniques, let's address the following. First, specify the profit function as a function of quantity. 2, set up the firm's profit maximization problem. 3, what is the value of Q that maximizes the firm's profit? We have to ensure the second order conditions hold so that this is indeed a maximum. 4, what is the what is the price that will prevail at this quantity? Call it P star. And then 5, what is the profit that the firm will earn at this quantity? Call it pi star. All right, so we're given these demand and cost structures, information on total revenue and profit. We're asked to answer these questions. So these questions are in a little bit of a different order than what we were used to when just solving a maximization problem. But that's okay. So this is what we're going to do. So the very first question says, or asks us to specify the profit function as a function of Q. Now I'm told that profit is total revenue minus total cost, and I'm told that total revenue is price times quantity. So I got everything that I need here, and this is already in price as a function of quantity form, this guy. So I just can plug in what I know. So profit of Q is going to be that total revenue minus total cost. So I'm going to get my price times quantity, right? This is, it's total revenue. And then I'm going to subtract total cost. My suggestion is to put total cost, the entire thing, in parentheses. This way you remember to carry this negative sign over. But here's my total cost. It's 5 plus 5 squared minus 2Q. So this is my minus total cost. Okay, cool. So we can draw this out. Well, we can, but we can. Let's simplify this. I'm just distributing that Q through. And now, because I have parentheses here, I've remembered to put this negative through all the way through the entire function. So you get minus 5Q squared plus 2Q. And I can simplify this guy. 126Q plus 2Q is 128Q. And then 3Q minus 3Q squared minus 5Q squared. So I'm just combining like terms. Is minus 8Q squared and then minus 5. So this is what I get for my profit function. And let me just put a box around this with a different color so we know. This is my final form of the profit function. All right. And then the second question says set up the firm's maximization problem. So what the firm's trying to do is they're trying to maximize profit. And you can write the entire thing out here, or you could just say max profit Q by choosing quantity subject to quantity being greater than or equal to 0. So we can't have negative quantities. So this is that firm's problem. All right. There we go. Ooh, whoops. And then the third one asks us, what is the value of Q that maximizes the firm's profit? Be sure to verify second order conditions. So this is just an optimization problem. I'm going to find that stationary point of this profit function, and then I'm going to ensure that it is indeed a maximum and not a minimum. So the first thing we need to do is set the first derivative equal to 0. I'm going to set the first derivative of this objective function equal to 0. That's 128 minus 16Q is equal to 0. And this yields a Q star equal to 8. So I have that the quantity that maximizes profit, or should maximize profit, is 8. So let's put a box around this guy. Final solution right there. But I need to ensure that it is a second order condition. So with the second order condition, for a maximum, for Q star to be a maximum value, the second derivative pi prime prime q must be less than 0. This is just the definition of what a maximum is. So let's calculate this. So pi prime prime q, so the second derivative of profit with respect to quantity, or likewise the derivative of this first derivative is going to equal negative 16, which is less than 0. It's less than 0 for all quantity. So I know I'm good. So this is indeed a maximum. We'll put a little check mark there. Here, let's move over here since we have a little bit more room. And then 4 asks us, what is the price that will prevail at this quantity? So, you need to use all the information you have here. So you're told that price is equal to 126 minus 3Q. So we can just evaluate this. So the price that will prevail in this market is just the price function, or the inverse demand function, evaluated at Q star. It's 126 minus 3 times 8, which is going to be 126 minus 24, which gives us 102 for the price. Let's put this here. Let's mark it off as a final solution. Whoa, so it's easy to read. And then finally, what is the profit that the firm will earn at this quantity? So in other words, what is the high value? What is that max value of profit? We're going to call it pi star. Profit star is just going to be the value of profit evaluated at Q star. So I'm going to plug in everything I know. It's going to be 128 times 8 minus 8 times 8 squared minus 5. And this is 1024 minus 8 to the third is 512 minus 5. So you get a profit star equal to 507. Okay. So we solved this entire problem without using any graphs. But let me show you what you just did very, very briefly. I'm going to go ahead and clear this page. Let me put over here what our Q is so that I don't forget. Okay. So I'm going to clear this page, and this is basically what we just did. If we were to graph out the profit function, right, we know it depends on quantity, and it's a quadratic function. It's going to look something like this. So this is the profit function. What we did was we found the point by setting the derivative of profit equal to 0. We found this point here, right? We found this point here. So at this point, pi prime q is equal to 0. So let's go ahead, and we found out with our specific function that this was 8. So this was our Q star. And then we plug that Q star back into the profit function, and we found out that it corresponded to a maximum value of 507. And then we checked to make sure that this guy curved downward, that it bent downward or was concave downwards by checking the second derivative. So let me just put here, I don't want to put f, I'll put f double prime of q is less than 0 for all q. Okay? Quiz yourself. Consider the following information. The firm's objective is to maximize profits. So read through the information given and the questions asked. They're similar to the problem we just did. And pause the video and try this on your own. All right, so for the first one, specify the profit function as a function of Q. So price times quantity is total revenues. That's 50 minus Q as the price times Q, and then total cost is Q squared plus 2Q. So when we simplify that, the profit function is 48Q minus 2Q squared. And set up the firm's profit max problem. What we're trying to do is maximize profit by choosing quantity subject to the constraint that quantity is greater than or equal to 0. 3. What is the value of Q that maximizes the firm's profit? Be sure to verify second order conditions. So we're trying to maximize profit. So the first thing I'm going to do is find the stationary point of the function. So I'm setting the first derivative of profit equal to 0. That yields 48 minus 4Q equals 0. I solve for Q and I get Q star equals 12. And then I'm going to ensure that this is indeed a maximum. We know that a maximum exists for Q star if the second derivative is negative. It is. The second derivative of the profit function is -4, and that's less than 0 for all quantity. What is the price that will prevail at this quantity? So I'm going to take Q star and evaluate it in my demand function, and I get 50 minus 12 equals 38. And finally, what is the profit that the firm will earn? So the maximum profit that this firm earns by producing at Q star is equal to 288. And now let's go ahead to cost minimization for a firm. Let's take a look at the firm's production decision using optimization techniques. Suppose we're given the following information. Q is quantity, total cost is 5 plus 5Q squared plus 2Q, and average total cost is defined as total cost divided by quantity. So using optimization, let's address the following. Specify the average total cost function as a function of Q. Set up the firm's average total cost minimization problem. What is the value of Q that minimizes average total cost? Let's call this guy Q star. And we need to verify our second order conditions. In other words, check the second derivative so we know that this is a minimum. And finally, what is the average total cost that the firm will incur at this quantity? Call it ATC star. All right, so now we're told the cost structure of a firm, the total cost structure, and we're told the definition of average total cost, which is this total cost per unit of output, and we're asked to address these questions. So let's start here. Specify the average total cost function as a function of Q. So look at the information that's given to you to answer these sorts of questions. So for the first one, I'm told that average total cost is total cost divided by quantity. So I've got average total cost depends on quantity, and that's going to be my total cost, 5 plus 5Q squared plus 2Q, all divided by Q, the entire thing, total cost divided by quantity. And I can simplify this guy, so I get ATC is equal to 5 over Q plus 5Q plus 2. So here's my average total cost as a function of quantity. And I'm going to put that in a box so it's easy for me to find later on. Okay, so then the second problem, set up the firm's average total cost minimization problem. So in other words, what are we doing in math terms? We're trying to minimize average total cost, and you can plug this in here if you wanted instead of just writing this general function. So we're trying to minimize average total cost by choosing some Q, subject to Q being greater than or equal to 0. And then the third one, it asks us, what is the value of Q that minimizes ATC? Call it Q star. Be sure to verify second order conditions. So the first thing I'm going to do is I'm going to set this derivative equal to 0. So I'm going to set ATC prime of Q equal to 0. This is going to give me some stationary point along the curve, along this function. And what I get is negative 5 over Q squared plus 5. Set that equal to 0. So when I arrange this guy, I can add plus 5Q squared over there, divide by 5. And what I get is that Q squared equals 1. And which yields a Q star either equal to 1 or -1. Since this is a constraint, we can't have negative quantities, this is the one that I choose. This is the one that's economically relevant. Both are mathematical solutions. But anyway, we get Q star is equal to 1. All right. Now the firm's trying to minimize average total cost, so let's just double check. Let's make sure that this is indeed a minimum. So remember, using that second derivatives test, to be a minimum, ATC double prime, the second derivative of this function, at Q star must be greater than 0. This is the second derivative test. So let's see. So the average total cost, let's see, the second derivative of average total cost is just the derivative of average total cost. That's this guy. Is going to equal, and you know what? Here's a little hint. I don't really like working with the quotient rule. So one way that you can rewrite this, I'm going to put this over here. One way that you can rewrite this is ATC prime is equal to -5q to the -2 plus 5. That's saying the same exact thing. So now I can use the product rule. So when I take the derivative of this, I get 10q. Now there's a q in here. What I need, all that matters for Q star to be a minimum and not a maximum, is for this guy to be positive at Q star. So I just need to see ATC double prime at Q star is equal to 10 times 1, which is 10, and it's greater than 0. It checks out. So this is indeed a minimum. And then finally over here, 4 asks us, what is the average total cost that the firm will incur? Well, I'm just going to plug in what I know. So my average total cost, the minimum average total cost, is just going to be that average total cost function evaluated at Q star. So I get 5 over 1 plus 5 times 1 plus 2, which just yields 5 plus 5 plus 2, which equals to 12. So that's it. So I just want to show you, let's make a little space here, what you're doing, or what you just did if you were to graph this guy out. Here's Q, here's ATC. If you were to graph this out, it's going to look something like this. And this is going to be my average total cost function. And what you did was you found the derivative. The derivative tells us the slope at any point along this curve. You set it equal to 0, which means you found this point. You found this point right here. So this was that Q star is equal to 1. And then we just reevaluated. We evaluated this function at 1 to ensure that, to find what ATC was, and we came up with 12. So this was that ATC star. And then to ensure, what we did was to ensure that this was a minimum, we had to make sure that the curve was bending upwards around Q star, which is the same thing as saying that F double prime, or the ATC double prime of X, was greater than 0, which it was. Quiz yourself. Consider the function below that relates total cost to quantity. The objective of the firm is to minimize total costs. Total cost is 6q squared minus 24q plus 50. Here are 3 similar questions that we just asked using different functions. Pause the video and try to answer these questions on your own. Alright, so for the first question, set up the firm's total cost minimization problem. So what we're trying to do is minimize total cost by choosing quantity such that are subject to quantity is greater than or equal to 0. To find the Q that minimizes total cost, we're going to set the derivative of total cost, marginal cost, equal to 0. We get 12q minus 24. When we solve for Q, we get Q star equals 2. And to ensure that this is indeed a minimum and not something like a maximum, we have to check that second derivative. The second derivative is 12, which is greater than 0 for any quantity of Q, including Q star equals 2. So that means that we are indeed at a minimum. And then finally, the minimum total cost that the firm will incur at this quantity is just found by evaluating the total cost function at that Q star, and this yields 36.